Hello, class. So in this video, we'll continue on section 5.3. In the last video, we were talking about the area function, and we talked about this first fundamental theorem of calculus, or part one, right, which was that given a continuous function on the interval AB, remember for us, continuous is the same as integrable. Right? So once you have a continuous function in the interval AB, we can define this area function, right, which we defined before. If you remember, the input was the right endpoint of the interval, right, or the upper bound of our definite integral. Right? So that's why you see a of x. You see that the variable's in the upper part of the integral sign, right? With the only restriction that x was inside our interval. So x is somewhere like that. Okay. Then this area function, right, is continuous on the interval AB. It's differentiable on the open interval AB. And as we saw, right, we derived that this sort of approximation in the previous slide, so that in fact it turns out that the derivative of the area function is the original function f itself, right? Meaning that a is an antiderivative of f on the interval AB. Now we're almost to the point where we can do this really nice trick to calculate definite integrals. So first, we have this theorem from before. So in section 4.9, what did we have? We said that basically two antiderivatives of a function differ by a constant, right? That's why when we write all antiderivatives of f, I want to write all antiderivatives of f of an interval, we write just one of them. Remember, capital F usually means antiderivative plus c, right? We know that we get all of these because all antiderivatives of f of little f differ by a constant, right? So we just need to, well, all we needed to do in section 4.9 was find one of them, then add c, where c was any arbitrary constant, and we had all antiderivatives. Okay? So by this note, right, we know, let's say f of x be any antiderivative for little f on AB. And of course here, as in the statement of the previous theorem, the fundamental theorem, we're assuming that f is continuous on AB, which again is the same as integrable. Then by the previous theorem, again, we know that any two antiderivatives differ by a constant, right? So what can we conclude? Well, we know that there exists some constant c such that, well, by using that theorem, f of x minus a of x equals c. So as we saw by the fundamental theorem of calculus, the area function is an antiderivative of f, right? Big F is any antiderivative. So we have two antiderivatives of little f. They have to differ by a constant. So we can write big F of x equals, just add a of x to both sides. Now, why am I doing this? And here's where the trick is going to come into play. Let's calculate, so let's go to another side. So here we just have, by using the theorem for 4.9, any two antiderivatives of a function differ by a constant, right? So let me rewrite this statement here. Right? So we had that f of x equals a of x plus c for some constant c. Now let's simplify this expression. What's f of b minus f of a? Well, let's see. By definition, what is this going to be? We'll just plug everything in. F of b, well, f is this thing, so plug in b for x. Right? So f of b is going to be a of b plus c minus, now we plug in a into the function f. Again, big F is given by this. So we replace x with a. So we get a of a plus c. If we simplify this, you have plus c minus c. And remember, here c is the same constant, because here we fixed c. C is the constant that makes f of x differ by c when compared to a of x. So here c is fixed. So some constant. So what do we get? So we get plus c minus c, those cancel, and we get a of b minus a of a. Now remember how the area function is defined. The area function is, well, the lower bound is always the left endpoint of the interval, right, which was A. So A of B is this, minus A of A. Remember, the input is the upper bound. The lower bound is always A, the lower endpoint of the interval. The input, again, is the upper bound of the integral. Oh, and sorry, I need to use T here. In the end, it won't matter, but for now, the way we have everything written, I have to use T. Okay. Now, if you notice, remember that we have this property of integrals, of definite integrals, which said that if you're calculating the net area or the definite integral on an interval, which is just a point, like as here we're saying we're calculating the net area bounded by f at the point A, that's 0. You can think of it because what's the length of that interval? Well, it's 0. Well, so it doesn't matter what the height is, right? It's always multiply 0 times any finite height, that's going to be 0. Right? So we know this is 0 by one of the properties we saw in the previous section. So what do we conclude here? See the equalities that we have. We conclude that f of b minus f of a equals the integral, definite integral from a to b of f of t dt. Now here, there's no more constant x on the upper bound, right? So here we can just use any variable we want. So remember, the reason why we were using t's before is because we had in the area function, right? We had the x here as the input, as the thing that's changing. So we had to use another variable for the function, right? So we use t. In this case, since we don't have since this is a constant now, it's not a variable, I'm just going to write it as a function of x. So go back to the previous variable. And now here is, if you look at these equalities here, this is telling us if we want to find the net area bounded by f and the x-axis on the interval AB, what do we have to do? Find any antiderivative, big F, of little f, evaluate at the endpoints, and subtract those values. It's as simple as that. As long as you can find one antiderivative of little f, evaluate that antiderivatives at the endpoint, subtract them, and that gives you the net area, the definite integral. And that's the relationship between antiderivatives and definite integrals. Right? That's why the notation for all antiderivatives, right, which we had here, that's why that notation is basically the same as the notation for the definite integral because they're related. Antiderivatives are related to definite integral. How do you find the definite integral of a continuous function? You find an antiderivative, and then you subtract that antiderivative evaluated at the endpoints. It's as simple as that. It's crazy, but it works. And you saw, I basically went through all the derivation. All I used was this theorem 4.9 and what the area function is, that the area function is an antiderivative of f. That's all I used, and we get this really nice result. And that's the fundamental theorem of calculus part 2. If f is continuous on AB, and f, big F, is any antiderivative of little f on AB, how do we find the net area bounded by f and the x-axis, which is the same thing as the definite integral from A to B? Just evaluate the antiderivative at the endpoints and subtract it. Now, that's the easy process. We'll go through over the examples. Notation-wise, we would do something like this. So this we have from the previous part. We just do this. Another way to write that is like this. So another way to write f of b minus f of a, or big F of b minus f of a. Another way of writing that is just write big F of x, draw this vertical line, which remember it means evaluate, and put as the upper part of that line, you put the upper bound b, and on the lower part, the lower bound a. So that's just notation that it's customary. So I'll do it in the examples because I think you should use it because that's the notation we'll use in the book. That's the notation you'll see everyone using. But the main idea is this, what we mentioned, right? Now we have a way to evaluating definite integrals. Okay. Now we're gonna go over some examples. I'm gonna do that in the next video. I'm showing you this now because you can go ahead and try it yourself and see how easy it is.